Hi, welcome to the Olympiad Geometry. Let's continue our study on Excenter. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe the channel. Here is a problem. The radius of circumcircle of triangle ABC is R. The radius of X circle in angle A is RA. Distance from excenter IA to circumcenter O is dA. Prove that dA squared equals 2 R squared plus 2R RA. So let's just draw the figure first. Okay, we have A, B, C. Right. So this is IA and this is O. Let's call this point as D. Right. We want to find, and we know that the radius of the X circle in angle A is RA, which means the distance from IA to line AB. This one is RA, right? And we want to find the distance from O to IA. Right, we call this distance as dA, and we want to prove that dA squared equals 2 R squared plus 2R times RA. So for this problem, the first thing we think about is that we already know that D is the midpoint of the arc BC, right? And we know that from the property of the excenter we discussed before, that BD equals 2, DC equals 2, DIA, right? So BD equals 2, DC equals 2, DIA. And if you look at the target equation that we want to find the dA squared, which is OIA squared, equals to something, right? So it just reminds us the Stewart theorem. So let me just give a short review of the Stewart theorem. Stewart theorem is saying that in a triangle ABC, P is any point on BC except point B and point C. We want to calculate for the line A, the distance of the AP, right? So we have that AP squared equals to AB squared times PC to BC plus AC squared times BP to BC minus PC times BP, right? That's Stewart theorem. So for this problem, we know that we want to calculate for the OIA squared, which is dA squared. And we know that OD is perpendicular to BC, and also OD, the distance of OD is R, right? And OA is R. So we can use the Stewart theorem in triangle OIAA and the point D, right? So we have OD squared equals 2 OIA squared times AD to AIA plus OA squared times DIA to AIA minus AD times DIA. right? So let's just use RA and R and DA to replace some segments here. The OD square, that is R square, equals to OIA square, that is DA square, times AD to AIA, plus OA, that is R square, times DIA to AIA, minus AD times DIA, right? So what we left here, we want to find RA, right? So that means we want to use RA, R, and DA to represent for AD, AIA, and DIA, right? So for AIA, we know that AIA equals to RA divided by sine half angle A, right? And for the DIA, because DIA equals to BD equals to DC, so for BD, the circular angle is angle BAD, which is half angle A, right? So the length of the BD can be calculated as 2R times the sine angle A divided by 2, right? Half of angle A. So we know the BD, which is DIA, right? That means we know the length of AIA, we know the length of the DIA, then we know the length of AD, right? AD equals to AIA minus DIA, that is RA2 sine half angle A minus this one, DIA, 2R sine half angle A. Okay, now let's just use these three equations to replace the AD, AIA, and DIA in this one. So we have R squared equals to DA squared times AD to AIA. AD is this one, right? That is AIA minus this one and 2 AIA, so which is 1 here minus 2R sine angle A by 2 divided by this one, RA2 sine half angle A, right? That's the first term. And the second term is R squared times DIA to AIA. DIA is this one, so 2R sine angle A by 2 to RA2 sine angle A by 2, right? That's DIA to AIA, and minus AD times DIA. AD is this one, so RA2 sine angle A by 2 minus 2R sine angle A by 2 times, that is AD, and the DIA is this one, so 2R sine angle A by 2, right? So this is AD, this is DIA. Now we just try to simplify this one. So we have R squared equals to DA squared minus DA squared times 2R by RA times sine squared angle A by 2, right? Plus R squared times 2R by RA times sine squared angle A by 2, right? Minus 2R RA, 2R times RA, right? And plus 4R squared. So I just write it as 2R RA times 2R divided by RA sine squared angle A by 2. Okay, this is the same as 4R squared. Just because we saw the 2R RA here. We saw the 2R by RA in other terms, right? So we just make it as this one. Then we just move the target equation to one side, which we have R squared plus this one, 2R times RA minus this one, dA squared, right? It equals 2 minus dA squared times 2R sine square angle A by 2. So this one is done. And plus R squared times 2R sine square angle A by 2. This term is done. And for this one, we have 2R sine square angle A by 2, right? Then it's clear. A equals 2 R squared plus 2RRA minus dA squared times 2R sine square angle A by 2, right? So we know that this equation, this one equals to this one, is valid for any triangle, right? It's valid for any triangle, which means it doesn't matter what the angle A is. This term is always valid. And we know that 2RA sine square angle A by 2 doesn't equal to 0. And it doesn't equal to 1, right? Then we know that this term, this equation, can be true for any angle A only if R squared plus 2RRA minus dA squared equals to 0, which means dA squared equals to R squared plus 2R times RA. Okay, so for this problem, we just use the Sturt theorem to solve it. It's a warm-up problem. It's not very difficult. I just want to show that we can, the Sturt theorem is a very, very powerful tool, especially in calculating for the distance square, something like this, right? And also, in this problem, we use our knowledge of the RA and let BD equals to DIA. That's all the properties we discuss about in previous videos. So that's it. This is a warm-up problem. It's not very difficult. I hope you like this video. See you in next one. Thank you.